like to start by just moving back here for a second to tell you a little bit about W.R. Meadows. W.R. Meadows was founded in 1926, our first manufacturing plant in Elgin, Illinois, just outside of Chicago. And today we're still a single-family owned and operated company. Very proud of our single-family ownership and almost 100-year-old history. We have 12 facilities throughout North America, 3 in Canada, and we've continued to grow to bring regional manufacturing to all points in North America. You can see some of our locations here. The yellow, the manufacturing facilities, 9 in the US, 3 in Canada, and the warehousing facilities as well across the country, strategically located for ease of operation and bringing products to you in the construction industry every day. Some of our Division 7 and 3 products. We're going to talk a little bit about building envelope products today, but we have a large array of expansion joint materials. Some of the first expansion joint material in the country was brought to you by W.R. Meadows. Concrete restoration materials, construction liquids, joint sealants, decorative concrete, as I mentioned, building envelope, and then soundproofing and insulation board from our sister company, Blue Ridge Fiberboard. For the below grade systems, just wanted to point out that we're discussing this today, but air barriers, self-adhesive flashings, vapor barriers and vapor retarders, primers, damp proofing, waterproofing membranes, and of course, drainage and protection course. So this is selecting the correct underslab membrane, an AIA HSW approved course. As a quick reminder, copies of this presentation will be uploaded to YouTube and available to you. If you'd like a copy, please contact us via the info@wrmeadows.com email address that you see on the screen now. Again, that's info@wrmeadows.com. And we will submit your credits to the AIA if you did provide us an AIA number, and they will be sent to you directly. So do give us a little bit of time on that, as there are plenty of people joining this presentation. And today, if you would please direct all questions to all panelists on the Q&A section in the lower right of the presentation. We will attempt to answer your questions during the presentation. However, if your questions require a lengthier answer, we may end up getting back to you all via email. So thank you again for joining me. This is an AIA accredited presentation at this point. As of the rules of the AIA, I'll be no longer discussing specific W.R. Meadows products and systems, but we're going to get into the course. The learning objectives: to identify and explain some of the moisture movement below grade and the resulting effects of uncontrolled moisture movement. We're going to identify other below grade contaminants that affect occupant health and safety, and understand the difference between an underslab moisture barrier, or I like to call it a waterproofing barrier, and an underslab gas barrier. We're going to determine the requirements for use of an underslab moisture barrier or an underslab gas barrier, make that distinction, and understand installation details to provide complete underslab protection. So let's get into some of the definitions. What is an underslab vapor barrier or retarder? We use the term vapor retarder because it's more correct in its definition, and it's really what the code defines essentially as a barrier to the passage of water vapor in the form of gas or bulk water. A material or construction that impedes the transmission of water vapor under specified conditions, typically wherever there's a delta between two sides of the membrane, we're going to see this employed. So again, what's the correct term? Do we use barrier? Do we use retarder? Chapter 2 of the code is always going to identify membranes as retarder in language, typically in 3 classifications: Class 1, Class 2, and Class 3 vapor retarders. So the correct term as per the code would be retarder, but without getting too off topic, we'll leave it at that. What is an underslab gas barrier? Essentially, a material designed to prevent soil gases such as radon, methane, and volatile organic compounds, or VOCs, from migrating through the soil and through the concrete into the occupied space. It'll also perform as a vapor retarder, preventing the passage of water vapor in the form of a gas. So not only are they preventing the passage of volatile noxious gases, it's also going to impede the passage of water vapor through a mode of transfer called diffusion. So what is an underslab waterproofing membrane? This is an impermeable membrane designed to prevent liquid water from entering a structure wherever we have a vapor pressure delta between two environments. We typically will have waterproofing. So depending on the material, it would also perform as a vapor barrier or a retarder and a soil gas barrier. So there are products out there that do perform both functions, waterproofing and vaporproofing, and have extremely low permeance for transmissions of soil gases that are commonly found in many urban areas around the country. And we're going to explore that a little further as we get deeper into the presentation. So why specify underslab waterproofing? Naturally, water infiltration and moisture diffusion renders interior spaces uninhabitable. Water and moisture problems are the single largest factor in limiting useful service life of a structure, and most importantly, can be detrimental to the occupants of the structure. For example, any sort of life, safety, health, and welfare matter, not to mention the effects it has on the interior finishes, which we'll discuss as well in a little bit. Benefits of an underslab waterproofing or blindside systems are that they greatly minimize high humidity levels in structures that are conditioned. Moisture contribution to microbial growth, mildew, and offensive odors. We know it only takes that magic ingredient, water, to foster microbial growth. Condensation is another matter, and finished flooring failures. Let's say that fast 3 times, finished flooring failures. For example, delamination, breakdown of flooring adhesives, blistering of floor finishes, tile carpeting problems, you name it. I think you get the picture. But breakdown of floor covering adhesives is key, and buckling of wood flooring. This is something not very new to pretty much everyone here. So how does water enter the structure? Obviously, site drainage, slopes towards a structure, irrigations, sprinkler systems, cracks in the concrete, improper waterproofing details. We're going to talk a lot about waterproofing details and continuity. For example, improper drainage around a home, hydrostatic pressure and high groundwater levels. That's probably the first order of business when determining if an underslab system is required, of course. I typically ask what the soil test or geotech report will indicate. Is there, soil that's going to work as a capillary action, like sandy soil that typically brings in water into our below grade area? It only takes a very gentle grade towards a structure to get water moving in the wrong direction. And as we all know, the code does identify or require a typical 1/4/12-inch pitch for waterproofing membranes or any type of membranes. So of course, the slightest grade towards a structure can allow a lot of water to accumulate. And illustration there of just accumulated water around a structure, which happens fairly frequently in residential homes around the country. So how does water vapor enter a structure? Again, vapor, which would be water in the form of a gas, enters where we have a vapor pressure differential between two environments, the outside environment being, in this case, the soil. The subgrade soil will always constitute a 100% RH, or relative humidity, and it's usually about 55 degrees down there below grade in the soil. And so if our below grade occupied conditioned spaces are maintaining a 70-degree temperature and a 50% RH, and the soil's at 100% RH, that 100% relative humidity is going to seek the lower humidity of the interior occupied space. And of course, a porous material like concrete's not a good vapor retarder. So why specify underslab gas barriers? Again, this is 072716 in our master format. numbers, below grade vapor retarders. Why specify underslab gas barriers, or as we refer to them in master format 072716, below grade vapor retarders? We want to prevent volatile gas vapor ingress into structures. We want to enhance the building life safety. We want to maintain compliance with standards typically in residential structures. And of course, limit future liability. Pretty simple and straightforward. So let's discuss some soil gases. We're going to talk about radon now. Radon is a naturally occurring gas produced from the radioactive decay of uranium in rocks and soil below grade. And it's common throughout the US. Radon is heavier than air. It's a colorless, odorless, tasteless gas, which can accumulate in a closed space. And it's the second leading cause of lung cancer in the United States. To continue with radon, the source of radon is through the soil, as I mentioned, with the breakdown of uranium from rock. The entry points are through cracks and gaps, basements, slab on grade structures, crawl spaces, and of course the stack effect and mechanical pressure that is created within a home just from the above grade to below grade systems connected to one another are also means that allow radon gas into the structure. So we're going to talk a little bit about methane now, another soil gas that's important to take a little time with. Methane's produced from the decomposition of organic material by bacterial action in the absence of oxygen. Emissions in the US decreased by 18% between 1990 and 2018. 60% of the global concentrations come from human activities. So livestock production is an obvious one. Methane is colorless, it's odorless, it's tasteless, it's lighter than air, and in concentrations, it's an asphyxiant as it displaces oxygen and is combustible. It's interesting that this is similar to hydrogen sulfide gas, which is commonly found in well systems and has similar effects on structures. And further on methane, as it relates to a soil gas, same entry point as radon through cracks, drains, utility penetrations, sump pits, injection pits. It can accumulate inside wall cavities, crawl spaces, and inside sump pumps and poorly ventilated basement areas. And it's considered non-toxic, but does not have permissible exposure limits like radon. But higher concentrations can be dangerous and would certainly be a fire hazard or explosion hazard at high level. We're going to talk about hydrocarbons now a little bit. Obviously, soil gases that would equal toxic chemicals. They have a wide range of organic compounds found in them and are derived from geological sources such as oil, coal, bitumen, and certainly abandoned oil production sites, which will introduce a lot of this to the ground soils. The most widespread soil contaminants in this category are commonly referred to as BTEX. So that would be benzene, toluene, and O-xylene. And these are the typical hydrocarbons that we find in soils and certainly in brownfield sites. There's a wide variety of problems related to BTEX, chiefly their toxicity, mobility, and persistence, and they're typically found, as I mentioned, in brownfield site developments. So a brownfield site development, according to the U.S. Environmental Protection Agency, a brownfield site development is, quote, real property, the expansion, redevelopment, or reuse of which may be complicated by the presence of potential presence of a hazardous substance, pollutant, or contaminant. That's from the EPA. So what should I use? consideration for selection of an underslab membrane. We're going to go through some of these different situations. What do we use when we find these types of contaminants in our soil? Are we dealing with bulk water or vapor? Are we dealing with soil gases such as the ones we just mentioned, radon or methane? Or are we dealing with toxic chemicals with BTEX, hydrocarbons, or all of the above? So critical properties of an underslab membrane include obviously waterproof, vaporproof, or gasproof, and the continuity, of course, and this alludes to the detailing as continuity, becomes one of the most important pieces then of the objective in placement of the membrane. If I were to give you one thing to take away from this underslab barrier presentation, it would be that you'll continue to hear me talking about it, but detailing becomes obviously very important with all of these systems, as with waterproofing, vaporproofing, and gasproofing. So they should have superior puncture resistance, which is natural for the assembly of these types of membranes. We're using a lot of reinforcing steel often above the membrane, which will challenge any membrane during its assembly. It's going to be compatible with the surrounding soil. Will it be robust and durable over the service life of the building? How easy is it to install? And this speaks to board stock versus rolled goods. Sometimes we have a substrate that's not particularly even, and we have to consider how easy it is to install that barrier. Can it serve multiple roles? In other words, can it serve as an underslab gas barrier, a waterproofing membrane, or certainly both? And there are materials out there that do serve both functions. They will be a little more robust and more costly, but sometimes that's necessary. So what needs to be done? Moisture control of liquid water. Let's talk about that. Obviously, controlling liquid water is a big factor. Liquid water control, when we're protecting the structure, we'll always want to be aware of the end goal, and our sights should be on shedding water away from the structure. As I mentioned previously, any slight grade towards a structure can allow water to build up. Even if the water levels are below the lowest point of the foundation, this can be a problem. Drainage is another big factor, and it's a nominal cost to a project usually to add a little bit more drainage to shed water away from our foundation. Capillary breaks are also another means to prevent water infiltration. And of course, providing an underslab waterproofing membrane, especially in urban centers with high groundwater. We want to bathtub a structure, especially those close to large bodies of water where groundwater levels are close to the surface. Very simple part of the hydrologic cycle, getting drainage correct and investing in it and investigating it. So what does a water control system look like for the protection from water damage to the structure? As we mentioned earlier, detailing is always critical to prevent the water from entering the structure. That means all of your ancillary parts and pieces to the main membrane. Of course, as mentioned numerous times, the continuity is the most important part of a successful below-grade application. Determine the requirements for the waterproofing material. Evaluate the material for water vapor permeance. Again, they're not synonymous, waterproofing and vaporproofing, and potential soil gas protection. The two will be different. Water vapor permeance will be based on E96, that's ASTM E96. There's several standards as well for gas infiltration and transmittance that we're going to go over. And when we talk about the details, again, this being the big takeaway, the two most important waterproofing principles as per Michael Kubal here are as follows. The first principle would be the 90% to 1%, meaning that most of the leaks result from 1% of an envelope's total exterior surface area, resulting in most of our issues. The second principle is 99% of the leaks are attributable to causes other than material or system failures. It's easy to assume the membrane is at fault, but most of our points of entry are going to be some type of penetration, either pipe, mechanical, or electrical. And certainly for above grade windows, walls, any penetration is usually the source of the problem. I'm a big proponent for following the guidelines of the NRCA, or National Roofing Contractors Association's Roofing and Waterproofing Manual. Any type of pipe penetration should have a minimum of a 3-inch offset where we can detail each pipe with proper flashing or tape with a minimum of 3 inches of that flashing or tape tying onto the penetration and 3 inches onto the substrate. In some cases, that might not be feasible. And in such cases, some manufacturers do allow the use of membranes to be used in a pitch pocket type of condition, or there's also the option to create a built boxed vault around a battery of pipe penetrations, as we see here. It's a lot easier to deal with right angles in a built box vault situation rather than detailing any type of membrane around all these pipe penetrations. Even in a pitch pocket condition, you can see how closely clustered those pipes are. It might be very difficult to get the bitumen or pitch or whatever you want to call it around each one. So that's probably more of a cost to do it the right way, but we want to make it as easy as possible to get the membranes installed and the ancillary parts shored up, and that's always going to provide a better quality deliverable to you and your clients. So let's talk a little bit more about waterproofing membranes. We find these in various compositions. HDPE carrier films, meaning high density polyethylene. You see them in low density as well. And these are types of films that we use, or a combination of that married to an, SBS rubberized asphalt, hydrostatic resistance to head pressure, the industry standard for underslab membranes and self-adhering sheet waterproofing membranes. It's typically about 231 pound-feet of head pressure below grade. That's the service ability of those membranes when we go below grade, 231 feet. The lower the water vapor permeance is preferable, obviously. Typically, we see waterproofing membranes in the class 1 realm of water vapor permeance. I referenced chapter 2 of the IBC, or let's call it the code for definitions of what a class 1 vapor retarder is. The lowest water vapor permeance is always going to be preferred. High puncture resistance, again, construction sites are not easy on waterproofing membranes. When we lay them down, we're doing a lot of work on top of them typically. So we want high puncture resistance. We want to consider membranes that have the best resilience and also protection against soil gases, which is something you'll determine from the geotech reports of the site, which we're going to speak of in a little bit here. So let's talk about water vapor and moisture control. Water vapor control is going to be determined by temperatures and relative humidity. I touched on this earlier. If there's an occupiable space and it's dehumidified, typically subgrade areas are often areas of high moisture content. We want to mitigate that, and underslab system is going to do that. High pressure always seeks low pressure when we're talking about vapor control. And so if the soil provides 100% relative humidity, and if our interior space is dehumidified to about 30% relative humidity, it's going to be a means for vapor movement. And that's always going to be independent of air pressure based on the temperature and relative humidity. And in this case, the use of a vapor retarder under the slab is a great way to mitigate that. Different industry standards. So for specification purposes, these are some of the industry standards for identifying different types of systems. So as per ASTM E1993-98, that would cover bituminous vapor retarders, ASTM 1745-17, plastic vapor retarders. This one is mentioned in the International Residential Code as acceptable as a vapor retarder. and ASTM E1643-18 standard practice for vapor retarders. And of course, at the bottom here, we have some ACI guides for concrete and floor slab construction, 302.1R15, and ACI 302R06, the revision in 06, the guide for concrete slabs that receive moisture-sensitive flooring materials. How are vapor retarders classified by ASTM? Well, ASTM E1745 for plastic vapor retarders. These are put into 3 classifications for water vapor permeance and their tensile strength, puncture resistance, and performance level. And depending on the use of the structure, whether it's a museum, a data center, a hospital, it's more than likely that it's going to be considering a Class A material for obvious reasons. Again, selection of a vapor retarder, conformance to ASTM E1745 Class A. Is 6 mil polyethylene really going to provide underslab vapor protection? Essentially, yes, it is, according to the International Residential Code, but consider it the minimal starting point. A Class A material would be a preferred way to go. This standard is primarily intended for use in above-grade building construction and on the interior of below-grade building construction, and this standard is not intended to apply to vapor barrier materials for use under concrete slabs or as ground cover in crawl spaces. So let's talk a little bit about vapor retarders. When considering these, we want to look for those with high-grade virgin resins as opposed to a recycled or reclaimed resin because it is a higher performing material. Choose those designed with low water vapor permeance. And you want superior tensile properties and, of course, economical characteristics, and those that can also be effective against radon and methane. Defining material standard for these barriers is according to ASTM E1745 and installed according to E1643. So we're going to talk about gas control next, specifically for radon and methane. What needs to be done in regard to radon and methane? Well, gas barriers are used as part of a full mitigation system, usually passive or active, and low permeance to radon and methane. A regular vapor barrier can be used, and although poly is acceptable, ASTM E1745 materials are preferable, and of course, continuity is the key, and floor and crawl spaces must be covered. What are the maximum exposure levels? And I'll preface this in advance by apologizing for my pronunciation of some of the scientific and technical terms. For radon in the US, the EPA identifies a maximum of 4 picocuries per liter, and Health Canada identifies a maximum of 5.4 picocuries per liter. The World Health Organization identifies very low at 2.7 per liter. For methane, there are no current industry-wide regulations. Most jurisdictions state 1% maximum. Again, greater than 1% as exposure can cause asphyxiation, and at 5% or greater, you have the danger of explosion. Industry codes and standards. For radon, see ASTM E1645, which would be the standard practice for radon control options for the design and construction of new low-rise residential buildings. ASTM E2121 would be the standard practice for installing radon mitigation systems in existing low-rise residential buildings. Notice here, this is for residential. And K1240295 for determination of radon transmittance will identify the maximum ability of the membrane to resist the transfer of radon through it. For methane, ASTM D1434, the standard test method for determining gas permeability characteristics of plastic film and sheeting to identify as a gas transmission rate. Industry codes and standards. I have to apologize. This presentation was put together by a colleague, and I'm just presenting it now. So we're going to go with National Building Code of Canada for 2015. Requirements for rough-in. 6 mil polyethylene allowed as a gas barrier for radon. That's the lowest standard and would advocate for better system. NRCC, test hut rivets or radon infiltration building envelope testing system has a material and systems testing based on ISO standard, which is 11665, which is a material testing similar to K125, the test method from the Czech Republic that we mentioned earlier. Industry requirements for radon and methane. Control of radon and methane requires a complete system. The gas barrier is one component of the system. And again, 6 mil poly allowed as a gas barrier for radon in most jurisdictions. There's no current industry requirements for gas barrier minimum permeance values as they exist currently. In the city of LA, they do have acceptable materials that will not exceed an average methane gas transmission rate of 40 milliliters per day. And this is all depending on what local codes are. So for toxic chemicals, let's get into some of those. Again, addressing brownfield sites. Brownfield site development, the environmental site assessment or ESA are a good idea, and a step-by-step analysis of the site outlined by the governing body to determine actual contaminants that may be present. You'll find these in your geotech report. The goal is to determine if there is anything in the site that will require further testing, resolve any issues presented by the initial study, and if contaminants are present, we're going to delineate the nature and extent of the problem, followed by a detailed plan for the remediation of the site, excavation, removal of contaminated soils to appropriate deposit sites, or implementation of the remediation solutions. What do I need to do if I have toxic chemicals? Determine if remediation is a suitable solution. Reaching out to a manufacturer to have them take a look at your phase 2 soil reports can be a way to start. If you see the gas barrier could be used as part of a full mitigation system, passive active ventilation. You want to find a barrier with low permeance to BTEX or petroleum-based chemicals in most cases. And of course, as mentioned many times, continuity is key in this presentation. Regular vapor retarders will not be suitable, the continuity of which is going to be very, very important. We're going to talk a little bit about soil gas barriers as they relate to the EVOH technology. EVOH technology is ethyl vinyl alcohol polymer technology. Again, that's ethylene vinyl alcohol polymer technology. These are designed with very low water vapor permeance. They have superior puncture resistance and tensile strength, and are highly effective against radon and methane transmittance. EVOH are also resistant to solvents and hydrocarbons, and do not assume high quality moisture barriers are going to be effective gas barriers. That is to be determined by the membrane. EVOH is really the top of the mark again. Reach out to your manufacturers to check with the lab based on your soil reports and determinations by the professionals. Just going to show you this graph here on EVOH and BTEX transmittance. The slide shows the effectiveness of EVOH membranes versus other films against the passage of gases listed in the illustration, and here quite obviously showing the superiority of the EVOH technology over low and high density polyethylene films in both the 40 and 20 mil thick range. But as you can see, the EVOH membrane is superior. Installation of moisture barriers. Talk a little bit about this. Site conditions and subgrade prep. This is a very important slide here for successful application of a barrier or retarder. Naturally, we want the membrane to be installed on compacted subgrade so it doesn't get compromised. Sharp and crushed rock have to be covered by compacted fill to avoid puncture. Of course, always refer to the ACI 302.1 R15 for subgrade prep, section 614, which is shown here. Proper preparation of the subgrade can make or break an installation of a membrane. And if you're specifying, it's important to include the ACI recommendations for proper subgrade prep. Basically, it's telling you here, if you look closely, the mix should not penetrate the surface more than ½ inch, or the voids that are there are going to be compacted to less than ½ inch. Membrane placement used to be more of a contentious subject than it's become currently, but contact with the underside of a slab or with a cushion or blotter layer was the question. There are certainly arguments for and against this type of layer, as it could lead to possible curling of the concrete and possible flooring failures. I think if you went out and discussed this and took a poll of what might be the most thoughtful and successful approach, you'd find that the majority of this work is being specified with the barrier in direct contact with the poured concrete. I think that most structural engineers and architects these days would agree. It's best to have the membrane in immediate contact with the underside of the concrete. But again, you're going to have to talk to that about with your engineer and their recommendation. Installation of moisture barriers. You see this again. Continuity is key. No punctures, fully taped joints and terminations. Certainly a well-trained crew by the manufacturer is ideal, and proper detailing of penetrations, as this is where most of the problems are definitely going to result from. Detailing, detailing, detailing. That's our running theme through the presentation. Image here of installing the overlaps correctly. It's also key. Again, pay attention to the transitions. The changes in plane are very important. Detailing penetrations and protrusions properly, all very important. Here we can see some of the detail work around these penetrations, which can get a little complicated with your detailing tape, but pretty straightforward and simple. Installation of gas barriers. This is the final part of the presentation talking about the installation of gas barriers. Continuity, of course, is key. No punctures, fully taped joints. In some cases, the side and end laps will require plenty of overlap. That's going to be per the manufacturer's requirements. Please pay attention to those. Proper detailing of the penetrations is key. Your manufacturer should be able to provide the necessary tapes for that part of the installation. This is part of a mitigation system, whether it's an active or passive system, and engagement of the NRPP, or National Radon Proficiency Program, or the NRSB, National Radon Safety Board, is of course recommended. Typical installation of a mitigation system. You want to use a clean course of granular aggregate below the slab to allow the gases to move freely underneath the building. That's the passive system. Seal all openings, the penetrations, the sumps, your ejection pits, the pipe penetrations, cracks in the concrete and foundation floor. Install a soil, gas, or vapor retarder membrane on top of the granular material, and seal all the overlaps, joints, and terminations of this membrane. You want to run a 4-inch minimum PVC pipe vertically from the gravel layer under the floor slab through the concrete floor slab, and cap and seal the pipe. We'll see some images of this in just a moment. The building must be positively pressurized when all ventilation and exhaust systems are in operation. long-term testing of the building if concentration levels exceed guidelines, installation of a full active soil depressurization system, which is typically an active fan that runs about 24 hours a day. So you can see here mitigation systems, just some images here of an active and passive system, images of the 4-inch PVC piping and the underslab vapor retarder as shown in the right corner there. Here's an image of an installation where we can see that minimum overlaps are key to a system's performance, or the making sure that the minimum is met is key to a system's performance. Again, following manufacturer's instructions. Installation of gas barriers as related to the overlaps. So illustrated here are two methods of overlap taping, the first for vapor retarders and the second for gas barriers. The tape seam over are 12 inches for the first with an additional for the second with an additional two-sided tape instead of a 6-inch overlap with the tape, which is for just the vapor barrier. A seaming tape with a low gas transmission is suggested instead of a common seaming tape for vapor barriers that employ the interest in low gas transmission. Passive or active ventilation, we're going to talk about both of those. Passive is a soil depressurization system. It's a lower cost system. It requires permeable aggregate, as we outlined earlier, and may reduce gas concentrations up to about 50%, and requires the system be designed to accommodate future fan integration where radon levels exceed 4 pci per liter or more, which won't be known until the system's been installed and then tested. Active soil depressurization systems will be a little higher cost, engineered with a fan integrated into the system, and will likely have service life maintenance. These systems are highly effective and may reduce gas concentrations by up to 99% when employed. So just illustrating here that an active soil depressurization system, if in the budget, is a sure way to make sure our system is going to work properly without added cost later. Ventilation options. This illustrates both passive and active systems. Passive on the left, far right showing an active system here with the fan. And in summary, there's a number of different types of systems available to determine the requirements. We need to assess water, vapor, radon, methane, solvents, hydrocarbons. Most economical and most crucial component is to reduce moisture problems and maintain healthy indoor air quality. We want to select systems accordingly and use proper application details. And with that, this concludes the AIA portion of the presentation. I want to give you a snapshot here of some of our WR Meadows below grade waterproofing and gas retarders. Precon 071300. We've got Perminator, Perminator HP, a number of different gas barriers, vapor barriers, and waterproofing barriers, as well as our original product and still quite popular pre-molded membrane vapor seal with plasmatic core, which to date still has the lowest vapor proofing qualities on the market. It is a board stock and isn't perfect for all applications, but we do certainly have sheet goods to fill in where that isn't applicable. For performance, you can see that there at the bottom. Again, if you're interested in receiving the presentation today, please email us info@wrmeadows.com. I would encourage you to drop questions into the Q&A, and we look forward to responding to you all via email. And I appreciate your time and attention today in joining us for the presentation. Thank you and have a great day.